Good morning, students. Today we are going to discuss IIT-JEE NEET Foundation. The topic is thermal expansion. So, thermal expansion comes under the heat. Heat is a form of energy, travels from higher temperature to lower temperature. Thermal expansion is the change in the length due to the supply of heat, increase of length or decrease of length, expansion increases of its original length. So whenever there is a application of the heat on the body, there is a change in the original length or change in the original area or change in the original volume. If the length changes, that is called linear expansion. If area changes, that is areal expansion or superficial expansion. So if volume changes, that is volumetric expansion or cubical expansion. So there are three types of expansions: linear expansion, areal expansion, volumetrical expansion. Linear expansion when there is a change in the length. So the constant in the linear expansion is alpha. So there is a change in length per original length per degree raise in temperature. The change in length per original length per degree raise in temperature. What we will call it as a coefficient of linear expansion. Alpha is nothing but coefficient of linear expansion. This alpha value is different for different substances. Different substance expand differently. That's why the alpha value, the experimental expansion of coefficient is necessary. For different materials, different expansion is there. That's why we need have a constant for every material, that alpha which explains that. And this is the fractional change in the length. Delta L means final length minus initial length. So final length, the final length, initial length, let us say L0, final length is LF. LF minus L0 is the delta L. Delta L is change in length per the natural quality. Okay, so natural length, that is, if it increases, the change in length is positive. If it decreases, change in length is negative. That you should understand. And another, change in temperature. See, initial temperature, there is a, let us take here, let us take L1 is the initial length of the, L1 is the initial length of the object at a T1 temperature. L2 is the final length of the object at a T2 temperature. You can understand here, L1 is the initial length, L2 is the final length. So delta L is nothing but here, delta L is L2 minus L1, and delta T is nothing but T2 minus T1. So initial temperature and final temperature, initial temperature and final temperature, the difference of temperature, what we will call it, delta T. So we can understand here, delta T is the change in temperature determines the fractional change in the length. So this delta T determines the fractional change in the length. So from that there is a constant. So that constant is alpha. Alpha is coefficient of linear expansion. Coefficient of linear expansion. See, coming to the next one. The expansion concepts. If you take thermal expansion, linear expansion in that. So the linear expansion, the application is bimetallic strips. Bimetallic strips increases its length due to the change in temperature. These bimetallic strips and thermometers, etc., these are all comes under the linear expansion of the different substances. Let us take bimetallic strips are used. Yeah. See, the bimetallic strips are nothing but, there are two different materials like brass and steel. So these two materials have same length and they join together. Brass and steel are joined together, bonding the two metals with a dissimilar coefficient of linear expansion, thermal expansion, different thermal expansion if they join together. If you start heating combinedly, so due to the different material expands differently. Brass will expand differently and steel will expand differently. There is certain change in the length will be there. So a typical pair brass and steel is a typical example of bimetallic strip, which is used in all instruments, like wherever you need cutoff current and etc. There such cases we are going to use these bimetallic strips. Whenever you increase the temperature, brass expands more, and greater expansion, which results greater bending will be there, the outside of the curve. So now colder than the reference temperature, brass contracts. Whenever temperature decreases, it contracts also. The shorter length puts on the inside the curve. Shorter length puts on the inside the curve. Here brass is the whatever brown color, and steel is some ash color. So brass expands in this way when you are increasing the heat. When you are decreasing the heat, so similarly the brass is going to expand in that manner. So you can understand from this. So different material expands differently. For example, if this particular substance is there in iron box or heaters, etc., if certain temperature reaches, automatically the system will be cut off. The entire closed system will cut off, and it breaks the circuit, and the utilization of electrical energy can be minimized. In that way, you can use this bimetallic strip. The bimetallic strip is the straight strips which are made to the coils to increase the sensitivity in thermostats, etc. Electrical breakers, just now I told you, electrical breakers which is going to be used. This is the electrical system, their circuit breaker. If there is a circuit is there, you can break or make the circuits. You can break or make the circuits. In that way, it is very, very helpful. So this is about bimetallic strips. See, coming to the linear expansion. In the linear expansion, the change in length per original length per degree raise in temperature is alpha value. The alpha values, if you try to find out for different materials, see different materials, different alpha value will be there. Let us take one calculation here. See, overall the small temperature ranges, thermal expansion will be there. The thermal expansion increase in length is directly proportional to change in temperature. The increase in length, let us take some values and we can prove it. The value, alpha value is this much for different, like steel. See, for different materials, different alpha values are there. This is the table for alpha value. See, alpha of glass is 9 into 10 power minus 6 per degree centigrade. If it is in Fahrenheit, 5 into 10 power minus 6 per degree Fahrenheit. So glass, ordinary glass is that, but Pyrex glass if you take 4 into 10 power minus 6. Aluminium 24, brass like that. These are the alpha values for different materials, like tungsten 4.3. All those are the thermal. See, alpha value for different tables. In that, this part only we are going to have. See, something like, see, coming to the heat and thermodynamics, there thermal expansions. So linear expansion, change in the length. See, initial length and final length. Final length minus initial length is change in length. Similarly, areal expansion. What is areal expansion? Areal expansion is nothing but increase in area. So due to the application of the heat, there is a increase in area. So the length and breadth, if it is there, aerially it increases. The total area will be increased. Initial area will be something due to the application of the heat. So there is a final area is different. That change in area is delta A. That delta A is, so change in area. So change in area. So for example, if you take linear expansion equation, L is equal to L naught into 1 plus alpha delta T. Areal expansion becomes, areal expansion is nothing but, area is nothing but, see, length, if it is a square area, side into side, side square, L square here if you take. L square is nothing but, if you apply square of this, L naught square into, if you expand 1 plus alpha delta T whole square. So 1 a plus b whole square, a square plus 2ab plus b square. If you apply that, 1 plus 2 alpha delta t plus alpha square delta t square will come. Alpha itself is a small value, alpha square value can be neglected. If you are neglecting the alpha square value, only we are going to have this. So it means that area, see, the area is approximately equal to, so A naught initial area plus 1 into 1 plus 2 alpha delta t, 2 alpha delta t. So it means A2 minus A1 by A1 into T2 minus T1. That is 2 alpha is nothing but, here the 2 alpha is the constant, the 2 alpha is denoted by beta. Beta is equal to 2 alpha. This is coefficient of areal expansion. Coefficient of areal expansion is beta. So beta values are depends upon alpha only. Beta is equal to approximately equal to 2 alpha according to this calculation. You can get this calculation. For example, if you take an application like, if there is a metallic sheet is there, a small hole is there at the some area. Now if you are increasing the heat on this plate, the hole also increases its original size. It may increase or decrease based on the application of the heat. So that change in area also we have to consider. There is a constant in this type of expansions, that is called areal expansion. So that areal expansion is denoted by beta. So larger, for example, see, you take here thermal expansion of an area can be calculated from the linear expansion. The tables of expansion coefficients, the table of expansion coefficients, just now we have seen the values of alpha values. Once if you know alpha, you can find out beta. So in that way, beta is equal to 2 alpha. Beta is equal to 2 alpha. Every linear dimension increases by the same percentage with the change in temperature. Every linear dimension increases, including holes. This assumes to be the expanding the materials are uniform. Expanding material. Let us take, if there is a square sheet is there, a small hole is there at the center. So if you are applying a heat, initially the area of the total object, it is A1 at a temperature T1. Now increase the heat, so temperature increases to T2, then area also changes, that is A2. So A2 minus A1 is the change in area, T2 minus T1 is the change in temperature. So this change in area is directly proportional to change in temperature. So change in temperature describes change in area. So that constant is called beta. Beta is nothing but coefficient of areal expansion or coefficient of superficial expansion. Coefficient of superficial expansion. So next, coming to the, see, third one is volumetric expansion. What is volumetric expansion? Increase in volume per original volume. If there is a change in, so volume of an object, if it is changes, so let us take, there is a, see, something like a jar, some heat is supplied to this. Initially there is a temperature, then after certain time there is increase in the temperature. Due to that there is a change in the volume. So that change in volume per original volume is directly proportional to change in temperature, or change in volume is directly proportional to change in temperature. Here that constant is called 3 alpha. So 3 alpha is the constant, that is called gamma. Gamma is 3 alpha, beta is 2 alpha. So alpha is to beta is to gamma is 1 is to 2 is to 3. This is the ratio. This is the ratio. In the case of you take the volumetric expansion, initially the equation, the L equal to L naught into 1 plus alpha delta T. So if you are applying cubing both sides, L cube is nothing but volume, the volume of a cube, side into side into side. So volume is equal to L cube, L naught cube, 1 plus alpha delta T whole cube, A plus B whole cube, A cube plus 3A square, 3A square B 3 plus 3AB square plus B cube. If you are applying that expansion formula for this equation, 1 plus 3 alpha delta T plus 3 alpha square delta T will come. So when you are taking these values, the alpha square is a negligible value, you can ignore that value. Delta, see, alpha square value can be neglected, very small. Alpha itself is small, alpha square becomes negligible. If alpha square is negligible, alpha cube also negligible. So it means these two terms are ignored. Once if you ignore these two terms, then volume is equal to V is equal to, see, V naught, delta V by V naught is 3 alpha delta T will come. 3 alpha is constant here. That constant is called coefficient of cubical expansion. Coefficient of cubical expansion. So here alpha, beta, gamma, these are the 3 constants. Alpha is coefficient of linear expansion, beta is coefficient of areal expansion, gamma is coefficient of cubical expansion. Alpha is to beta is to gamma is equal to 1 is to 2 is to 3. Volumetric expansion values, this is the volumetric equation. So by using this you can calculate the values. So thank you very much. Thanks for watching this video.